Hello and welcome to this presentation on antiderivatives and indefinite integrals. Alright, so antiderivatives. So let's consider the following. If we take the derivative of f of x is equal to x squared, we will get, well, f prime of x is equal to 2x. Now let's reverse that. Suppose we have the function little g of x is equal to 2x, and we want to find a function capital G of x such that if I take the derivative of capital G of x, that'll give me little g of x. In other words, we want to find a function capital G of x such that its derivative is equal to 2x. From the previous example, we saw that capital G of x would be x squared. So the function capital G of x is called the antiderivative of little g of x. And the notation for the antiderivative is this elongated s, that's your integral symbol. This is the integral of capital G of x dx is equal to little g of x. And again, the notation says the antiderivative of capital G of x is little g of x. Now let's go back to that original example. So we had f of x is equal to x squared, and its derivative, f prime of x, is equal to 2x. But let's also consider the following functions. Let's say we have g of x is equal to x squared plus 3, and h of x is equal to x squared minus 5. If we take the derivative of those two functions, well, the derivative of g of x is also 2x, and the derivative of h of x is also 2x. So these two functions, their derivative is the same as the derivative of f of x. So when we try to find the antiderivative of 2x, what we're going to have is a lot of possible antiderivatives. And the reason why is because the derivative of a constant gives us 0. So to take that into account, what we're going to do is the following. If I want to take the antiderivative of 2x dx, then that's going to equal the x squared plus some constant. Now we're not going to know what that constant is necessarily, but we do have to account for it. So all of the antiderivatives of 2x are going to be off by a constant of c. So if you take a look at f, g, and h, the only thing that they differ by is that constant. So let's take a look at some antiderivative rules. Since the derivative of a constant is 0, the antiderivative of 0 is going to give us a constant. Since the derivative of f of x is equal to a times x, if I take the derivative of a times x, I get that coefficient of a, then that means the antiderivative of a constant a is going to be a times x and then plus some constant. Alright, so let's take a look at our power rule for derivatives. If you remember the power rule for derivatives, what we're going to do is we're going to bring down the exponent and subtract 1 from the exponent. If we reverse that rule to turn it into an antiderivative rule, then that means the antiderivative of x to the nth power dx, what we're going to do is we're going to add 1 to the exponent and divide by the new exponent. And again, don't forget your plus c. So to find the antiderivative of x to the nth power, we add 1 to that exponent and we divide by the new exponent. So let's take a look at a couple of examples of the power rule. So if I wanted to find the antiderivative of x to the 4th power dx, I want to add 1 to the exponent, so that makes it an x to the 5th, and then I want to divide by the new exponent. So I get a 1/5 x to the 5th power plus a constant. Let's take a look at another example. Let's say I want to find the antiderivative of x to the negative 3rd power dx. So to find the antiderivative here, we add 1 to the exponent, so negative 3 plus 1 gives me a negative 2, and then I have to divide by the new exponent. So 1 divided by a negative 2 gives me negative 1/2 times x to the negative 2 exponent plus c. If we have something like this, find the antiderivative of x to the 1/2 exponent. Now, if you recall, a 1/2 exponent, that was the same thing as a square root. And if you also remember from our derivative rules, we did not like working with square roots or cube roots. We like turning everything into fractional exponents. Well, the same thing is going to apply here for antiderivatives. So, the antiderivative of x to the 1/2 exponent, I add 1 to the exponent. 1/2 plus 1 gives me a 3/2, and then I divide by the new exponent. So 1 divided by 3/2 times x to the 3/2 plus a constant. Now 1 divided by a fraction, well, the way we divide by fractions is we're going to flip that fraction, so that becomes a 2 over 3, and then we multiply. So 1 times 2 over 3 gives me 2/3 x to the 3/2 exponent plus c. Now here's one of the neat little things. Whenever you take an antiderivative, you can check your answer by taking the derivative of this answer and see if you get what's inside of your antiderivative notation. Alright, so let's take a look at some basic rules for antiderivatives. So what this is this is going through all those derivative rules that we saw, well, not all of them, but many of them, and doing the antiderivative of them. So here I'm doing the antiderivative of some of our basic functions. So the antiderivative of 0, that is a constant. The antiderivative of constant is going to be that constant times x plus c. The antiderivative of x to the nth power, well, we just did that one. Well, we add 1 to our exponent and divide by our new exponent. Alright, the antiderivative of e to the x is going to be e to the x plus some constant. So if you remember our derivative rule for e to the x, the derivative of e to the x was e to the x. So the antiderivative of e to the x is e to the x plus some constant. Well, if our base number is not e, the antiderivative of some base number to the x is going to be 1 over the natural log of that base number, and then times b to the x plus a constant. Alright, if you remember, the derivative of the natural log was 1 over x. So the antiderivative of 1 over x, which is the same thing as saying x to the negative 1, the antiderivative of that gives me the natural log of the absolute value of x. Now notice we have absolute values here. The reason why we have to have absolute values is because x has to be a positive number in order to calculate a natural logarithm. And then my plus c. Reversing the 6 trig rules that we saw for derivatives, well, the derivative of cosine was negative sine, so the antiderivative of sine gives me a negative cosine plus a constant. The derivative of sine was cosine, so the antiderivative of cosine gives me a sine plus a constant. The derivative of tangent is secant squared, so the antiderivative of secant squared gives me tangent plus a constant. And the same thing all through down this. So, since the derivative of the cotangent of x is negative cosecant squared, the antiderivative of cosecant squared is going to be negative cotangent. Since the derivative of secant is secant times tangent, the antiderivative of secant times tangent gives me secant plus a constant. And then the last function that I have on this is cosecant. So, since the derivative of cosecant is negative cosecant cotangent, the antiderivative of cosecant cotangent gives you a negative cosecant. Now, those are the derivatives of some basic functions. Once you have those memorized, then those rules can be applied into these rules down here. So, if I have the antiderivative of some coefficient times a function, f of x, where f of x is one of these things above, then if I have a coefficient in front of it, then I can take the antiderivative by just still keeping that coefficient in front. So we saw a derivative rule like this as well. If you have a coefficient in front, then the coefficient in front stays in front. And you take the antiderivative like you normally would. Now, if we have two or more of these functions that are either added or subtracted together, and we have to take an antiderivative, then we do the antiderivative term by term. And again, we kind of saw the same thing with derivatives. We can take the derivative term by term. We can take the antiderivative term by term. Now, the last thing I want to point out here is there is no antiderivative rule for the product rule or the quotient rule. And in fact, there is no product rule or quotient rule for antiderivatives. So, we're going to have to work with just the rules that we have. And in a future lesson, we'll see something called the U substitution, but we are not going to see a product rule or a quotient rule for integration because they do not exist. Well, thank you for watching this lesson.